here are some final questions on field strength and potential. So have a quick read of these, have a good go at them, and then we'll have a look at the answers. So pause now. Right, hopefully you've had a good go at these. Let's have a look. 1. The surface of a metal sphere is held at a potential of 8,000 volts. So, sphere, 8,000 volts. Is the sphere positive or negative? Is it positively or negatively charged? Well, this is plus 8,000 volts implicitly. Here's 0 of potential all the way off at infinity, and here's our positive test charge. So if it's positive, it means we're doing work bringing this test charge towards it, so that means the charge on it must be positive. So the sphere is positively charged. Now it says add equipotentials for 6,000 volts and 4,000 volts. Well, the first equipotential can be any distance you like. There's a difference in potential of 2,000 volts between the surface and that equipotential, but then the equipotential must be circular. The next equipotential must be further away. So the 4,000 equipotential must be further. So this distance here must be less than this distance here. Maybe not quite so exaggerated as that. That's what I'm looking for. So circular equipotentials with the gap between the equipotentials increasing because it's an even increment of potential of 2,000 volts between each one. Question 2. Field strength is the potential gradient. What is the field strength between these plates? What's the potential gradient? How does the potential change with distance between here and here? Well, field strength, electric field strength, is literally the gradient, the change in potential divided by the change in distance. Now we had used delta R when we were talking about a radial field, but this isn't a radial field, so R doesn't make much sense. So maybe we'll call that D for distance. Well, it's quite simple. It's just the change in potential going across between these plates, which is 10,000 volts, divided by the distance moved across, which is 0.15 meters. If we give that a go, divided by that, we get a horrible answer of 6.7 times 10 to the 4 volts per meter, which is an interesting unit. The other unit for electric field strength is obviously newtons per coulomb. Either of those would be fine. So that is the field strength between those two plates. Now, interestingly here, we don't have to worry about these deltas being small like we did before in the radial example, because this is a uniform field. The electric field strength is constant all the way throughout this field. So these deltas can remain as big deltas. We can use that entire 15 centimetres here. We can use that entire distance in this calculation without any worries, because the electric field strength in this case is constant. So we don't need to use small deltas.